Hey, and welcome back to Mechanical Systems Design. Today we are going to talk about what happened in Project 2. And one way to do this that I think is pretty effective is just to walk through an example design process, the one that I used in designing my test parts when I was setting up the project. Now this video will be a little less tight than our usual topic videos, so feel free to jump around and watch it at a faster speed. So yeah, let's do that. Let's walk through an example process of creating a part. So the first thing that I usually do, and I think this is very often a really effective step when you're setting out to design a new mechanical element, is to really just think about, before I make any clever decisions about what the component is going to be, what do I know about the component just from the nature of the task itself? And so, when we set up this problem, we've got here the table. We know we want this offset load that's going to be applied by string with 100 newtons of force downwards, and we have this bounding box that limits where we can place our part. Just from those constraints and from that loading, we can tell some interesting things about our component. So a good way to get to these insights is to start with what I like to call the potato free body diagram. So, we know we got the table there, we got the rope over here, there's some boundary here, and let's just say we kind of fill the whole thing with material. What would we get without making any decisions really about our design yet? Well, let's see, what will we know from this? We've got this downwards force that we have to support. So if we're going to achieve static equilibrium, we're going to need an upwards force. And the only place that these forces can come from is the table. So there must be some kind of upwards force. Now, these two forces are offset. So we're not in static equilibrium yet. This thing would want to spin, right? It would accelerate clockwise without anything else. Now, if we could get that reaction force over right on top of the rope force, then we would be in equilibrium and everything would be okay. But we specified that this rope force has to be offset from the table by some amount to make it a little more challenging. And so we cannot bring those two things into alignment. Well, how will we get static equilibrium? We're going to need another force. And for example, a reaction force downwards that is offset to the left of the upwards force from the table. Now, many times when we first start these things, we might say, think about the component as clamped to the table or just, mounted to the table or something like that. And it's really important to recognize that intuitive way of understanding that the two things don't move relative to each other. It really means that if you try to move them, some forces develop. The only way that our part knows the table is there is because of the interaction forces between them. And so drawing that out explicitly is really, really helpful in understanding the kind of loading your design will experience and then what your design should look like. So just from this potato free body diagram, we can start to understand some things about our component. First of all, we would like this upwards reaction force to be as close to the edge of the table as possible. That minimizes the moment that the downwards force from the rope has about that center of pressure of the upwards force. Secondly, it might be helpful to have this force pretty far to the other side, pretty far off to the left. And why might that be helpful? Well, if we do a moment balance about this point, we're going to get this force times the lever arm. That will create a moment. And the only way that can be reacted out is by this force times this lever arm. So this force will be this lever arm divided by this lever arm times that force. And it's a very common sort of equilibrium problem that we will run into over and over again in these kinds of systems, such that if the longer that this lever arm is, the smaller this reaction force needs to be in order to react out the moment caused by that force. And oftentimes, a smaller force is beneficial. For example, in this problem, R1 here will equal F plus R2. So if R2 is smaller because it's farther off to the left, then R1 gets smaller too. And we'll see later why that can be really helpful in reducing the size of the structure associated with R1. Another thing that we could see here, oh, actually, I should say, you might have gotten tangled up about friction. So I said, oh, the only way you can react out that moment is with this downwards force. But what if there was a friction force here and maybe a friction force over here? Those things could also help to counteract the moment from our string force. It's true. But if we do a little bit of maybe just sort of order of magnitude analysis here, we're going to see that the contribution of the friction force is going to be kind of small compared to the contribution of these reaction forces, at least with the kind of geometry we've got here. So one thing to keep in mind is that the friction force, if we're not moving, would be at most mu Fn, right? So the maximum friction force we could have pulling off to the left at R1 would be coefficient of friction times R1. And the coefficient of friction is usually less than 1. In this case, for these materials, it's something like 0.1 to 0.3. So that gets you a much smaller friction force than your normal forces. And the other thing to see is that the lever arm for that friction force is going to be small compared to the lever arm, at least the potential lever arm of these normal forces. And so both of those two things put the friction at a disadvantage for overcoming the moment created by the rope. Another thing to think about is, do we need friction in order to achieve static equilibrium? And the answer there is also, it's going to turn out to be no, right? We haven't drawn any friction forces here, but we can achieve equilibrium in this case. And then the third thing to think about is the assumption of no friction a conservative or optimistic assumption? And in this case, it will be turn out to be a conservative assumption. So if we assume no friction and solve for what these reaction forces need to be, we will get bigger reaction forces, normal forces here, than we would get if we included friction, because these forces arise as a result of the need to counteract the moment caused by this rope force. Well, the friction forces would also help counteract that moment. And so if we remove those friction forces, then these forces have to get bigger. So all those things say, it's not too big of an approximation to friction, and it's a slightly conservative approximation. So we could probably work from there. All right. So now we've got kind of a free body diagram about for this really generic design, this potato design. We can also learn some other things about it. One thing is that this material up here in the upper left isn't really doing much for us. It's not carrying its weight. We don't want a reaction force over here. If R1 were way over here, that would be bad, right? We'd get a much bigger lever arm for F and a smaller lever arm for R2. Not good. So we want R1 to be over here, and we don't need all of this stuff. And so we probably want this to be kind of big. We don't want to have this. We want this reaction force to be as close there as possible. So that's actually quite a lot of information about what our design ought to look like just from a free body diagram of the most generic shape we can imagine. If we keep going along this line of thought, we can develop some additional insights. So let's first think about the implications of this free body diagram for the material around R1. So we want an upwards force on our part. So we need some bit of the component that pushes down on the top of the table. It would be nice if we could like screw into the table from the bottom, then we could just apply the force right where we wanted it. Or if we could have material that goes straight from here down to the rest of our component, but we can't because we can't pass through the table. And so we end up with something that's has some material touching the top of the table, and then it kind of jogs over and connects to the rest of the part. And we're calling this the hook element of the component. Well, just from this, we can understand some implications for what this section of material will experience. So if we draw a free body diagram of it, we've got that reaction force in the vertical direction. And as we saw just a minute ago, that reaction force is going to be big. That's going to be, something like twice the magnitude of the rope force, or bigger if that left-hand side lever arm is smaller. So we've got this big upwards force. If we're going to have static equilibrium, we're going to need an equal and opposite downwards force on this component. And what we can see right away is we don't have static equilibrium. This thing wants to spin clockwise. So where we've cut the material down here, we're going to need a moment. So this bit of material is going to undergo bending. And to keep that moment, bending moments, we try to avoid them often in these mass efficient design cases because they tend to develop high stresses on the edges of the material and low stress in the middle. And that tends to result in not very mass efficient design because the middle part isn't really carrying its load. They also tend to result in high stresses because you can kind of think about it as this bit of material doesn't have as much of a mechanical advantage over the centroid as this other bit, and so it's at a disadvantage. So we know as a sort of a heuristic that we'd like to try to avoid bending moments, but because the table is here, we can't avoid it completely. We've already sort of put things as close as possible to each other. So we're going to have some moment. And then let's think about what's going to happen when we apply a moment to this part. Well, it is going to bend, right? And so here I'm just drawing the stick figure version of the hook. And let's say this bottom part were perfectly fixed, which isn't really what's going to happen in the real system, but it's a good starting point. If we apply that upwards force, we're going to get a lot of bending in here in this section of material. And the whole thing is going to kind of both move away and rotate relative to the table. So what will that mean about how the table and our part interact? Well, we're kind of assuming a normal force at that contact between our hook component and the table. But if that hook component is right on the corner of the table and we do have a normal force, then that force will have both a vertical component and a horizontal component, right? And that, if we sort of zoom out and look at the full system, that will try to make everything move away from the table. We don't have any horizontal force that could react this out from the rope. The only other place that we could get a horizontal force that could help us would be friction from that second contact point on the bottom of the table. But if the horizontal component of this normal force is too big, then mu Fn won't be big enough to keep the piece in place. And we saw lots of our designs ran into this issue of as some load was applied, eventually the component would fly off the table and it isn't broken, it just slips off. So what can we do about this? If we really understand why this is happening now, that it's about this deformation due to bending, changing the nature of the contact force between the hook and the top of the table, maybe that can give us a trick for keeping this thing from slipping off. And we saw lots of different ways of trying to deal with that, including, things that look like they were intended to increase the friction, like, a bumpy surface, or, kind of really long pieces that are intended to, as it bent away, you'd still have contact. But it's really, I think, the thing that I've focused on here is the fact that this surface that's contacting the table is at an angle. What I want and that the contact point is at the corner. What I want is, I want contact on the flat part, the horizontal part of the table. And one way to try to do that is to change the shape of this hook element so that there's a gap in here between the table and that component, so that as it deforms and bends away, the contact point is still inside from the corner. So it's not right at the corner where you would get that the normal force with the horizontal component. So that's one thing that we could do to try to prevent that possibly foreseeable slipping failure mode. If you didn't see it when you were setting up your design, that's okay. That's why it's so valuable to run a low fidelity prototype early on in the process, so that you can identify failure modes you hadn't considered, but turn out to be really important. And I think we talked about this a little bit in our coaching sessions, maybe a week out from the due date. And this is always a good idea, as you start to really get your feet under you in one of these design problems, to make sure that you've kind of engaged in all the different tools available to you to some degree. Some sketching, some back to the envelope analysis, but not too crazy deep, not pages in algebra, but qualitative stuff like what we've just talked about. Some sketch FEA, where you pop it into the finite element analysis and see, does the deformed shape kind of look like what you expected? And printing something, testing it, and seeing if it behaved qualitatively, approximately the way you had expected. And if not, that can be a great sign, something you learn from, to go back to some sketching and hand analysis to figure out what's going on. All right, so we've got this little, we know a lot about our part at this point. We have done our potato FBD. We've gone a little deep on this hooking element. And now we can use an approach for developing the whole structure that I like to think of as connecting loads in space, or sometimes holes in space. And so we have, we know this thing is going to be there, and we've analyzed that a bit. So let's look at the rest of it. If we've got this downwards force, this should be a little higher, but this downwards force from the string, we know we're going to need this downwards force over here from some contact point with the table. And then we're going to have this, this surface here that'll have an upwards force and a moment. And, it's pretty hard to get away from any of these features of this problem, right? And if you look at this, it kind of reminds, hopefully, of some of those mass efficient design sketching exercises that we did in our topic video and in our coaching sessions, where we say, all right, we've got this force over here and this support surface over there. How do you connect them together? Well, and this is a lot like that. So this would be a great template to work from for, say, sketching out 20 different shapes of the whole system, to start to see what kind of things would make a lot of sense. And there are lots of good solutions to that problem. I'm going to just talk about a couple of variations that I happened to work through when I was working on this problem. And here's one. And we saw this in several of our designs with a common overall shape. And the logic of the shape becomes clear as you break it into pieces and look at some qualitative free body diagrams. So first, we've got this bit that we've already talked about. We've got this offset load, so this is kind of a cantilever. And we're going to have, we want some finite area to touch the table. We don't want to scratch our nice table. And then we need to move quickly to a very tall cross section here. Why a tall cross section? Because sigma equals my over I, and I, if I say have a rectangular cross section, but it's always true that the height has a disproportionate effect, I might be 1/12 base height cubed. So making the thing tall makes the area moment inertia big fast with the least amount of mass. So I want this thing to be kind of tall on this face. Now this part okay, my moment's gonna get a little bit bigger because of this offset, but it's close to being a constant moment through this part. So it wants to be tall and consistently so. And then we have these two arms that stick out. And each of these is more of a cantilever situation. So we have a point load here, and then an equal and opposite force up here with an internal a bending moment at the surface that's internal to the component as a whole. And because we have this bending moment here, there again, we're going to want things to be tall. Over here, there's no bending moment or almost none, and that tends to result in lower stresses. So probably our cross section will be smaller, and they'll be dominated by cross-sectional area. F over A will be where we get our stress. And this is exactly the same. So that's why we, if you noticed, flipping through some of the designs, we ended up with a lot of shapes that look like this. Now let's think more about the details of these arms. What should they really look like inside? Well, if we want a high area moment of inertia, we'd like to get lots of material far away from the centroid. And I-beams are really good for that. And so are box beams. The thing that is desirable about both shapes is that you see you've got this material that gets to be pretty far away, and that there's a substantial amount of cross-sectional area here. And if you wanted to make it bigger, you could maybe even thicken the top and bottom surfaces to increase that. Why a box beam instead of an I-beam in this case? Well, the way I think about it is there are two good reasons in this case. One is that our 3D printers are pretty good at box beams, and they like to print things where you have a shell with some infill, a small amount of infill, and so it's sort of compatible with the manufacturing process that we're using. If you really want to keep it truly hollow on the inside, you can use clever little tricks like printing with this surface on the bed and then modeling a few little thin little beams across the top that create a surface to print on. The other thing is that a box beam is really good at resisting torsion. So if I take a square rectangular tube and I try to twist it, that you generate this shear along this surface. And so, there's some shear force, shear stress here, shear stress there, shear, and that sort of circle of the shear creates the moment to resist the torsion you're applying to the thing. If you do that to an I-beam, it's much less good. For the same amount of cross-sectional area, it's much, much less effective at resisting torsion. Sort of like if you have a piece of paper that you roll up into a tube and then you tape the edges and then try to twist it, it's quite good at resisting torsion. But if you leave the edges open, it twists very easily. And it's a complicated topic, but there's some good, you can find some good resources in your textbooks and online on this. But so for those two reasons, that box beams lend themselves well to 3D printing. There's no support material needed, and that won't need to be removed. And because they're good at resisting torsion, this seems to be a good solution for getting our large area moment of inertia for resisting that primary bending load. And we talked a little bit about why this should be small. If we take this a little further, though, we might even be able to do better still. And something to notice is that when I draw this little curved arrow here to indicate a moment, what do I really mean? I mean that there is this uneven pattern of stress where up here the material is in tension and down here the material is in compression. And those two different loading types lend themselves to slightly different structural shapes. And so you might take this triangle box beam and break it into pieces where you have like a little strap up at the top that's just a solid cross section that's in tension, and that'll be very mass efficient for providing that tensile load. And then on the bottom you might have this compressive thing. Now if we didn't have to worry about buckling, then this bottom compressed element could look exactly like the top compressed element, and would be very mass efficient. But we do have to worry about buckling because this section is in compression, and whenever we have compression on any piece of a component, it's possible that it'll want to pop out, or in this case, maybe sort of do something out of plane. And so to prevent that, we're going to want some good cross-sectional area moment of inertia per unit area, and that again points us towards a rectangular or square cross-section tube. And the nice thing about doing this is that as we separate the top and the bottom further from each other, if we do our free body diagram, we'll see that the forces get smaller as those two are at a steeper and steeper angle. Smaller force, less cross-sectional area, less mass. Smaller force, lower critical force that's needed from our structure to prevent buckling. And those are both good things for mass efficiency. Now, of course, if we make it too steep, then it'll have to go very far away, and that gets longer and longer. That hurts us for buckling, and it hurts us for mass. So some moderate angle is going to probably turn out to be best. It's hard to do that when we have this solid cross section, because as we make this side taller, these faces get longer and longer, and they, add more and more mass to our part. So separating them out can be useful. All right, so if we put all those ideas together, we get a shape maybe that looks something like this. And this was one of my first just guesses at a design. And I think this is actually a slightly more refined version of the sketch. I don't think I captured my first sketch of this, but throwing in something that looks like that hook, constant cross section here, thin little straps, and then these compressed members that are hollow. This, this is hollow, this is all hollow to prevent buckling. So things look pretty consistent between the finite element analysis and my back of the envelope analysis. That gives me more confidence that I'm understanding the problem well. In this case, one of the important decisions we had to make setting this up was how to run a quick finite element analysis. We can't just apply forces at all three places, because then the slightest imprecision or numerical error will send things shooting off to infinity. SolidWorks won't run the analysis. So we have to do some kind of fixturing. In this case, I've fixed this face and then carefully calculated the forces that need to be applied here and here to achieve static equilibrium. And I actually use the evaluate measure tool in SolidWorks to measure the precise distances between these things where I was going to apply my load. And a little tiny imbalance in that force can actually have a really big impact on the deformation of the structure and its peak stresses. So something to be careful about. But the deformed shape looks okay. I've sort of rotated this a little bit so that we're looking at it from the perspective of the table. If I just kept this as it first ran, the whole thing would be rotated a little bit counterclockwise, because there's a force over here and a force over here. But that's not quite what's going to happen in the real system, where this part will be constrained in its height. And you can see that that hook is tilting and tending to pull away from the table edge, but hopefully, given the size of the fillet on the table that I happen to be using, that won't cause too much of it. Won't be so far that it falls off. Well, then I ran the test, and I don't have a video of this original test, but what I found is that when I just quickly made a part, printed it to make sure things were working the way I expected before refining, I underestimated how much that top hook would bend, and it flew off of the table, just like we saw in a lot of our designs when we printed them at home and tested them. And so that gave me a signal that, okay, this is a really important, perhaps dominant failure mode, and something that I need to make sure that my part is really responsive to. And I came back and made a few tweaks here. So here's a different way of reacting out that moment from that top hook element. Instead of having that long piece that all experiences bending, where the whole thing can bend, and then every bit of that bending contributes to it pulling away from the table, I thought maybe we should try to create some sort of more like 3-point bending situation. Maybe we'll have just a strap. Those are mass efficient. I love those to pull down. And then on the other end, we'll have this big lever arm, and we'll just push up a little bit at the rope contact point. And if this lever arm is big, then that force over there could be pretty small. And if you put all that together, you end up with something that looks like this. So here we have, and let me blow it up for you because this qualitative free body diagram really helps to understand why things are like this, what they're intended to do. So to solve that problem of the maintaining contact with the top of the table, we've got this element in 3-point bending, big force down, pretty big force up, just to the left of it, and a smaller force over here, far offset up. We've got a tapered cross section because we expect this is, if I cut here, this thing is kind of like a cantilever, and the bending moment is getting smaller and smaller as you get towards the tip. We have those same compression and tensile elements that we talked about before to create that moment to support those endpoint loads. And then in the middle, we have these skinny little straps to hold things together. We need to apply this downwards force here, and that is going to be really transmitted down all the way to these bottom elements. These are kind of pulling against each other, and these are kind of pulling against each other. So that results in a structure where the center pieces are pretty mass efficient, and then we've concentrated our buckling resistance and bending resistance into bending into this, and then buckling into those bottom elements. And so if you put that together and start to work on the details and refine it a little bit, you end up with something that looks a bit like this. And here you can see this nice, even distribution of stress on these central straps. That's good. And we can fine tune the thickness of the thing to get that just right and avoid having too much mass there. These ended up being pretty short in one direction and a little taller in the other direction because of the primary buckling mode. So here you can see how when this top part bends, it's not pulling out away from the table as much. Here was the primary buckling mode. So for the buckling analysis, I set it up really similar to the stress analysis. And you can see that it looks a little funny. This is fixed in this view, and I can see the top surface here and the top surface there. So what we've got is one of these classic out of plane buckling situations where if we look at it from the top or the side, it's a little clearer. Because we're pushing down on each side, it kind of wants to tip so that it gets a little easier to bend in the way that those forces would like it to. So it kind of pops out and bends down is the way to think about it. And so in order to pop out, though, it needs to, you can see how this section is really bending like that. And so these straps could have any cross-sectional shape we'd like. They could be square, or they could be tall, or they could be wide. And because this is the dominant buckling mode, it made the most sense here to make them really thin in the vertical direction and really wide into the plane direction, because that gives you the best area moment of inertia for resisting this type of bending. And this is a good way to do this. You can look at the way that the shape of the buckled component, and it gives you insights into which pieces, which parameters you can tune to make the part stiffer in that direction. And then the stiffer something is, the higher the critical force before it buckles there. And as I was tuning these things, I was playing back and forth between two buckling modes. So this is the dominant one, but in order to maximize resistance to this buckling mode, you want to make all these elements short and wide into the page. But eventually, if you do that, you run into this buckling mode where it's buckling in the plane. And this is more similar to what we're accustomed to seeing when we think about buckling, where these compressed elements are sort of popping out in the middle. So by this cross section, I was iteratively selected to have a reasonable balance between these things. And when testing this, this is what it looked like. So here we have the final component. It weighs, this one's about 7.6 grams, and it failed at about 24.3 pounds. And here you can see it, that element that is in 3-point bending, ooh, yeah, that deformed a lot more than I was expecting in the real part. It may have something to do with the way that I set up the print, the way it was sliced. And so if I wanted to make this even lighter, I have lots of ideas based on this last test. And actually, even making this presentation today, I was like, oh my gosh, there are several things. I want to try this. I want to try this, which is I have to hold back and focus on getting project 4 set up instead, which will also be fun. But that's just a sort of a quick walkthrough of how this process can go. So you're really blending all these things together to try to really understand your part while you make it better. So you can see we're using some sketching, some back of the envelope analysis, finite element analysis, and prototyping. And it's really important not to just do this sequentially, not to think, I'm going to sketch, I'm going to analyze it by hand, I'm going to analyze it in CAD, then I'm going to make it, and then I'm going to be done. It does not work that way. You have to like sketch and then do some back of the envelope analysis and learn from that and say, oh, well, this is problems, or, oh, this implies I should really make this, I should eliminate this thing, or make this thing really small, or make this thing really big. And doing the finite element analysis, just like a quick up version, really helps in making sure that I'm not missing big things in back of the envelope analysis. And same with prototyping, with low fidelity prototypes early on. That's super helpful. And what you're really trying to optimize for, it's tough when we're first learning mechanical systems design. It's tough to know which elements to use when. And that's actually one of the things we're trying to help you learn how to do. As you think about optimizing this process, what you want to do is learn the domain as fast as possible. You're trying to figure out, what is the task implying about how my part will be loaded? What does the loading imply about what shape the part should have? And you're not really trying to get to the most detailed analysis with any of these techniques right away, but instead really learn about the problem. So that's just one overview of one person's design process. Hopefully some of these things resonated with the experiences you had in this project, or maybe resolved some of the questions you had lingering about project 2. I hope that you're able to carry this on into project 3, and especially project 4, where we'll be using mass efficient design again.